Fantastic. All right. So I have to allow this to be recorded. So just a little bit more background on myself. I'm an agricultural engineer by training in soil and water conservation engineering. During my undergrad and grad studies, I took way more soils classes than most engineers do. Plus, I took the engineering ones too, geomechanics and structural soils in the civil department. And then I had a 10-year run at ODNR, where I'd still be if it wasn't for the case administration. They moved my position to Ohio EPA and wasn't really where I wanted to work or doing what I wanted to do. And the role that I had with DNR, Justin Reinhardt, if you guys know him, is basically doing those responsibilities now for Ohio EPA, and he's doing a fantastic job. All right, I've got way too many slides, so I'm going to rush through some of them. We will make a PDF of the slides available to people later, so if you don't catch something, you'll be able to look at it. This was the original title that Tessa and I had agreed on. After I thought about it a little bit more, I was thinking more about talking about soils and their potential contribution to stormwater management, and maybe thinking about what our expectations are and what they could be. A couple of quick acknowledgements. Stu Schwartz, I don't know whether any of you caught a webinar that he did for Franklin Soil and Water last week. He's a good friend and one of the leading people in the US on understanding the impacts of urbanization on soils and ways that we can recover hydrologic function in them. And I've borrowed a number of his slides today. So the ones that I've borrowed from Stu all have a light brown background. I want to make sure that he gets acknowledged for that. And then also in the run up to this, I had a couple of questions on soil stuff, and I'm just grateful. We have a bunch of really exceptional soil scientists in the state of Ohio. You have Matt Deaton sort of down this way that many of you probably know, Jeff Glanville at NRCS state office, and Neil Martin, who I used to work with at DNR, helped me on this presentation. You can quickly read through this. I just wanted to outline what I'm going to cover today, really talking about soil profiles, construction effects on soil profiles, how we quantify soil hydrologic function, a couple of ways to manage soil hydrologic function, and some last thoughts on measuring the impacts that we're getting in terms of green infrastructure from our soils. Just in defining soil, I want to contrast that the soil is not the same as the underlying parent material. It's been altered by the interactions of climate, relief, living organisms over time. So this is what a soil profile typically looks like. This is a lot of Ohio soils look like this, with not so much the O or organic horizon at the top, but an A horizon, B horizon, C horizon, which is parent material that may either be glacial till or decomposed bedrock. And again, formation of a soil from the parent material over time involves what the parent material is, but then landscape position, biology, soil biology, effects of climate, and all of that over time. This basically is pointing out that the soil that you get is a function of all of those things. It is unique to a place. In a certain place, we may have a lot of the same soil because all of those things are sort of in common. And this process of getting from parent material to an actual functional soil profile takes at least hundreds of years, typically thousands of years. The soils that we have in Ohio, most of them are at least 10,000 years old in their formation. That's natural soils. Less so in urban areas. The place that isn't, the soils are not that old, would be where you have erosion coming down slopes on top of old soils, and you're forming new soils on top of the old soils. And then in stream valleys, we have alluvial soils where the floodplains are formed out of alluvial materials and sort of ongoingly forming new soils in alluvium. Just some quick factors. These are soil forming factors that I just want to go through real quick. I just think it's neat stuff. The western half of Ohio has limestone bedrock, and so we would expect soils in the western half of Ohio to have higher lime content. Soils in Ohio are most affected by glacial geology. The slide on the right shows the extent of the Wisconsin glaciation, which ended just over 10,000 years ago. And as you can see, that lines up with maps of glaciated and unglaciated areas. And sort of the middle map there shows that unglaciated Appalachian Plateau. The glacial map of Ohio gives more details. It's not just all till plains in there. There's some end moraines and canes and eskers and all kinds of fun glacial geologic features that affect soils locally. Everybody knows that Southern Ohio and Eastern Ohio has a lot more relief than Western Ohio. That affects a lot. And I was just mentioning that in unglaciated areas, we basically have three soil types, those that are called residual soils that develop from the material in place, colluvial soils that are developing or have developed in material that has either creeped down or eroded down the slope, and then alluvial soils in stream valleys. Soil forming factor, all of Ohio is in what's called the human continental. It's warm summer, cool winter kind of climate. So that's within Ohio, that's not going to cause a lot of variation with our soils. Talked about the living organisms as factors. All kinds of neat things are happening in the soils. I'm putting this in here because it's such a good graphic. And then vegetation is one where mostly what we had here was deciduous forests. In Ohio, there's a little bit of prairie area west of Columbus there. And you'll see this when we get to the dominant soil types, that our soils will be dominated here by soils that developed under woodland versus the prairie soils that developed to the west of us. One thing that's really makes a difference in those soils are the plants, the vegetation that's present there. And I just think it, again, such a nice graphic. This shows prairie roots that are going down to 15, 20 feet in a lot of places, and the density of them. And in contrast to that, that's the root structure of turf grass. So you can see in terms of building soil or maintaining soil structure and organic matter content and biological communities, turf grass is somewhat limiting. It can do a pretty good job shallowly, but not to the same extent that other aggressively rooted grasses can do in particular. All of these taken together end up giving us some common soil types. Most of Ohio, again, is dominated by, not seeing my pointer. So what we have here, these are the prairie soils out here that reflect prairie vegetation. And what we have in Ohio really is these are woodland developed soils for the most part, both east and west, but what we have is the glaciated area. So these would typically be in soil survey parlance alpha sols. These would either be inceptisols or altisols in southeast Ohio. So we end up with the soil regions of Ohio where each one of these colors has sort of similar soils across the landscapes there. Again, Western Ohio, these are high lime glacial till developed soils, low lime glacial till soils, unglaciated area out here. And sort of along here would be Illinoisan or pre-Illinoisan glacial till soils. And some of you may be familiar with some of the crappy Illinoisan soils that we have in Warren County, Clinton County, Claremont County, the Avonburg, Blanchester, Claremont, Ross Moines, that make me want to live elsewhere. So just all of that taken together, again, once we get into a particular location for soils developed on glacial till, we might have a landscape that looks like this, where it goes from a Miamian at the top landscape position through Salina, Crosby, Lewisburg, down to either a Brookston or Kokomo in the lower lying position. It's all pretty predictable based on the soil forming factors. And in an area that's not glaciated, what we have there are the residual soils at the top of the slope, the colluvial soils developing in eroded material and alluvium. Lots of good information on that. I just wanted to give that as a little bit of background, thinking about everything that goes into creating a soil profile naturally, and including in that aggressive vegetation to the full rooting depth, plus at least hundreds, typically thousands of years. Okay, so we're going from intact soil profile, natural soil profile. And during the development process, typically what happens is topsoil is removed and stockpiled on site. Sometimes it's taken off site and repurposed. Excuse me. This organic matter in the soil is at odds with some of the structural goals on site of having stable soils for roads, pavement, sidewalks. So the easiest thing to do is just to get all of the organic matter, all the topsoil out of the way, and work with soil that is easy to work into structurally sound compacted soil. That's a real goal of development on sites. So what we're losing with that is under a natural soil, we've got a lot of very positive things here that are providing a healthy plant environment, but also a very functional hydrologically soil surface. Almost all sites treated now the same way, except for large lot residential, where the initial land grading pretty much looks the same. We're just creating a surface on the plan that we want to support whatever our development's going to be, with the roads, driveways, other infrastructure, any buildings on the site. And I mean, this is all just pretty common to us, right? All the pans, bulldozers, sheep foot roller, all of these are either mixing up soil, moving soil, or compacting soil. The end result then ends up looking like this, our finished soil surface at the beginning of development. And on that, that graded surface of mixed up subsoils, we either sod it, we may apply 3 to 4 inches of topsoil, typically replaced from the topsoil stockpile on site, or depending on where it is within the development, it might go for landscaping. So these are just 2 examples. On the left is seeded and mulched. On the right is just where sod's been laid. So I want to look quickly at this in terms of thinking about this and the vegetation that we favor in urban environments and the recovery of anything that looks like a functional soil profile. So I start with these photos were taken from a site in Westerville, a new development, like 2013, plus or minus about 10 years ago. And the entirety of the soil profile is this. Everything here has been turned into parent material. And so the entirety of the soil profile, I measured it, was 2.5 inches. So your sod is your A horizon, but also your entire soil profile. And you say, well, once the grass starts growing, it's going to start to make soil out of the rest of this material here. This photo in the upper right is from my parents' house in Columbus, in a neighborhood that butts up against Upper Arlington, just northwest of Ohio State. And their house was constructed in 1969 with this same type of construction, grading and construction. And what's interesting is you can still go into their lawn and stick your thumb down through the entirety of the soil profile and pull up the sod that was placed in 1969. And it's interesting. So a result of that, and I'll talk about this a little bit in a second, is you basically have about 2 to 3 inches of soil profile to support your lawn. Lawns are much more important across the municipal boundary in Upper Arlington, but here, a lot of people basically irrigate and fertilize constantly to keep the grass green and looking like the Scotch lawn photos. When it rains on my parents' lawn, the water rides down the surface of the compacted underneath soil and comes out at the edge of the curb. So it's almost like it fills up whatever the water holding capacity is of that 3 inches of soil. And then basically what's underneath is impervious. And it's very similar to just having a paved area. So I just want to say that there we have 50 some years already with almost no recovery of any soil function. So what we have from the development process is starting with an intact soil profile. In the end, what we end up with is a very little bit of surface soil on top of parent material. The organic matter is removed. This is the most beneficial part of the soil for rhizosphere health, for plant health, for hydrologic function. It's just gone. The organic matter serves as a soil conditioner, plant and animal food, and the glues. All of that facilitates creating soil structure, which allows good things to happen hydrologically, and most of the soil's nutrients are removed. The soil is crushed, mixed, and compacted. All of the soil structure is destroyed. And the soil pores that were there are all compressed, and the interconnections between the pores are lost or shrunk significantly. So we get less water storage, less ability to pass water in the form of saturated conductivity or infiltration. And they both tend to be drier and wetter at times of the year than we would like our soils to be. In essence, what we've done with the soil profiles, we've reduced it to compacted parent material. You may see the term eudorthant in soil surveys. Basically, it is what's typically used for entisol type soils in urban environments where we have no diagnostic horizon, there's no profile development. We may have a little bit of an A horizon. But what we've done is we've taken our soil profile from a fully functional and developed soil profile, and we've regressed it back hundreds, probably thousands of years. Where I'm going to go with this is we can, at the very least, in our development process, we can protect this, or in our regression, we can do more of this kind of, this second level of soil profile development. All right, with 2 to 4 inches of topsoil, our plant available water is greatly reduced, soil nutrients are removed, and underlying compacted fill material is unpenetrable to plant roots, including grass roots. And here's just an example of that. These 2 lines, the first one is where the cone index is a measure of pressure that it takes to get through a particular soil, a pressure pushing on a cone-shaped rod. And so this first line is where we would expect to get some limitation of root growth. And this second line is where basically roots would be unable to grow through that layer at all. And so what we're seeing here with the TS, the most right and upward, the orange set of measurements is from a site in Maryland that went through the development process, and then they just played topsoil back on top of that. And so what you get is a root environment up to a depth of about 2 to 3 inches. Again, that sod layer, where you have environment that's conducive to root growth and function. Everything below that is basically too compacted for the roots to even explore that layer, or to do anything to change that layer. So in these kinds of environments, your plant health depends on constant feeding of water and fertilizer and elevated maintenance needs and the costs that go with that, even to keep a healthy vegetative community on the lawn. All right, so this next section is on quantifying soil hydrologic function. These are a bunch of properties that are used to describe in some way hydrologic function. And I think most of these are going to be familiar to you. Hydraulic conductivity is the rate at which water moves through a soil profile. Infiltration rate is going through the soil surface. Soil water characteristic curve is something that describes the connection between the soil pores at different pressures. Storage volume and drainable porosity, plant available water all sort of go together. That's how much water can we get into the soil profile that's then not going to be runoff. How much water is going to be there. The drainable porosity is in between events. That's how much will drain from saturation to be available for the next rainfall event. Typically, it drains within about 24 to 48 hours. And plant available water, of course, is how much water is going to be there to support our plant community. Every one of the properties in reds is highly dependent on soil bulk density or the level of compaction. And so this is just one illustration of that. We have 2 topographic curves here showing infiltration rate on the left on sandy urban soils, on the right more clay urban soils, more typical of what we would have in Ohio. And what you see is going from native profiles to compacted profiles, we have an 80 to 90% reduction in the infiltration capacity of those soils. Another way that gets used quite a bit to quantify soil hydrologic function is through the use of pedotransfer functions. And pedotransfer functions are soil properties, but they're soil properties that are hard to measure, where we use soil properties that are easier to measure or readily available, for example, in a soil survey, where we can take those properties, and there's some empirical relationships or regression equations that allow us to use easy to measure properties to get harder to measure properties. Rosetta is one that a lot of people use. I use the soil water characteristics calculator all the time. This is what the interface of that looks like. Basically, you start by entering your sand and clay content. This gets you soil texture. And then you have some levers over here that you can manipulate to represent what you have in terms of soil compaction and organic matter. So with this, you can take a normal soil profile, change the texture from what's typically there with a silt loam or loam topsoil to what typically becomes a clay loam or silty clay loam, new parent material that we're putting down, and then reducing the organic matter. Typically, it'll be in the 3 to 5% range in native soils. After development, it's less than 0.5%. And then the compaction level can be adjusted from normal to dense to hard. Typically, we can look at a 5% or 10% increase in compaction and see what that does. All of the empirical relationships that allow us to estimate these hydrologic properties. What we end up getting out of that then are all the hydrologic properties that we want. Typically, what we're most interested in is the saturated hydraulic conductivity, but we also can get the wilting point and the field capacity and saturation. All of those allow us to calculate plant available water capacity and drainable porosity, which are also useful properties. The relationships that those are based on are empirical relationships that are documented by Saxton and Rawls. And here's just one example. This one, I think, is in the NRCS Soil Survey Manual, where basically it shows 4 different textures and densities what the hydraulic conductivities are. Unfortunately, NRCS is putting their hydraulic conductivity rates out there in micrometers per second. And I'm not sure if there's a single person on the planet, even the people that put the tables together, that think in micrometers per second. I always have to convert it to inches per hour or something I can understand. All right. In quantifying soil hydrologic functions, I just mentioned pedotransfer functions. There are also the next level of complexity up are soil hydrology models like Hydrus that use data inputs and can use real weather data and use infiltration and water distribution equations to change the level of water throughout a soil profile over time. And then for engineers, we all use hydrologic models of some sort. The simple method is the one that the R sub V equation in the state stormwater manual is based on. Infiltration models like the Greenhampton-Horton are used in the SWIM model in the National Stormwater Calculator, places like that. And almost all of us use the curve number method for either design or review of development impacts and stormwater calculations that determine sometimes the size of conveyance infrastructure, but always used for developing the storage and release characteristics of detention basins and practices like that. I'm just throwing the runoff reduction method in here too. It's not a model. It's more of an accounting system that uses empirical estimates. But it is a way of tracking hydrologic function of, and basically the runoff reduction method is a bunch of practices that are mostly like green infrastructure that uses soil. Probably the main thing I wanted to communicate in this was soil hydrologic function and the curve number method, and how poorly we use this currently, and the possibility of being more honest with it and using it to develop a system of credits that would result in actions that gave us better soil profiles. The curve number ends up with a runoff depth that is a function of what's called storage. It's the total abstraction, which is a combination of the initial abstraction plus ongoing infiltration. And that number comes from a curve number that we pick out of a table. And so the hydrologic function there, what we get out of it are these initial abstractions, and total abstraction tell us how well a soil is functioning hydrologically, or a site overall. And so having accurate hydrology based on the curve number model depends on having honest and good faith estimates of the curve number. It really needs to fit the site and soil conditions. So are the hydrologic soil groups that we're using for post-development soil, are we picking the right ones? And the same when it comes to hydrologic condition. So we want to get into that a little bit. Hydrologic soil groups have been tightened up in the way they're defined, and there's a table in the National Engineering Handbook, which is a combination of depth to impermeable layers and hydraulic conductivity and the most limiting layer. So it's pretty much an exercise of what's measured in the field on the soils, and there's a soil database that lets them assign that a hydrologic soil group value to each soil in a soil survey, including the web soil survey. So impervious area, it's pretty easy to pick a curve number. It's 98 across the board, but then typically for post-development conditions, the default is for the engineer to just select open space in good hydrologic condition. And so this is reviewing back on what we get with the development process. They're saying it's equivalent to pasture in good condition. On the left here, we've got pasture in good condition. On the right, so this is pasture in good condition. Typically, the value that engineers use for post-development open space is equivalent to those values. Does this equal that? So what's the problem there? If that's being done, there's a breakdown somewhere in the system. Again, I bring up my parents' house. The curve number, even though it was probably designed with a curve number of 80 or possibly 74, the curve number is probably still over 90 today. Higher means more runoff, lower means less runoff. So what we're saying here by choosing open space in good condition is we have these very high initial abstractions of water. That is the amount of water that the soil is going to capture before any runoff happens at all. So we're saying for some of these soils, it's going to take a 1/2 or 3/4 inch of soils. In reality, that's not what we're seeing at all. And so again, we need to sort of follow what's in the fine notes in the TR55 guides. So again, the curve number values were developed on the assumption that pervious area is equivalent to pasture in good hydrologic condition. Obviously, that's not the case. They do have this little blurb on disturbed soils here, which basically says if the soils are disturbed, that doesn't hold. That doesn't keep people from doing it. And so if you have disturbed soil profiles, you should no longer be using the Web Soil Survey soils and values for your curve number inputs. At that point, unless the entire profile is silt loam or loam and uncompacted, that's not what we're getting. This might be a pre-development soil on the left. On the right, the totality of our silt loam here is about 2 inches. And so we're not getting that surface function. So at the least, we should be using the subsoil and using that value. In the rainwater manual, everybody for their post-construction curve numbers should at the least be using the appendix out of the rainwater manual that has pre and post-development hydrologic soil groups. Even that is inadequate because that's all based on provided that significant compaction has not occurred. Well, we see with all of those photos and what's happening that's the compaction has occurred. So what's our alternative to that? And this is more looking forward than where we're able to operate right now. The next few slides are all going to be from Dr. Stu Schwartz and the excellent information that he collected. So the urban soils that are compacted above natural bulk density are anywhere from 90 to 100%. Those that are above 5% higher bulk density is around 90% of those soils, and above 10% compaction. You see vacant lots, athletic fields, you're still at about 80% based on the samples they've collected. So what they've been able to do using the Hydrus model is to do some modeling. So basically, just topsoiled shows that almost all of the curve numbers in their soils, except for a sandy loam, a sand, and a loam, all of those were in the range of a curve number of 90. But they have come up with a way of restoring a soil profile that allows them to have a much higher infiltration content. And so that reflects in the Hydrus model results with what we could end up using as credits over here on the right. The difference in runoff depth between 1 year storm, I'm just going to use an example for a silty clay loam, typical of Ohio soils, is by doing the soil restoration, you're going from a curve number of 88 to a curve number of 67. This is real soil hydrologic function that we're adding back in that allows us to remove 0.8 of an inch from that 2 inch storm, an additional 0.8 of an inch. Okay, this is where I wanted to stop. I only have a few slides left, but I wanted to ask you that I've got some goals in my own mind that are my goals for assessment, management of soils in an urban landscape. I want to know what your goals would be for managing soil in an urban landscape.
Because that's increasingly stormwater management goals, because with just a couple inches of available soil for even infiltration, it seems like it seems like the stormwater management practices would be overwhelmed fairly quickly with the traditional designs of those. And we're seeing more flooding and those kind of hurdles with neighbors next to development and things like that. So I would think that if we understand soil or amend soil or respect it during construction, those stormwater control features would be more effective or work the way they were meant to when we understand what we're doing to the soil that impacts that design.
Anybody else have something? Feels like when I'm teaching my class, it's like there's always one student that's willing to speak up. Okay, since we don't have that much time, that I think encapsulated like a number of the things that I have here. You know, so one of the things that you know, there's some people that don't believe in climate change. I live in a farming community where none of my neighbors believe in climate change, but they talk about how weird the weather is every year. So you know, what I'm seeing is when I look at the historic rainfall data, we're getting more rainfall every year. We're getting deeper volumes in our big rainfall events and higher intensities in those. So that's a trend that's happening. I get a different story from utility directors, service directors, city engineers, county engineers. They're seeing it. So, you know, the result of that is flooding, down cutting of urban streams. All of those things are real. Water quality impacts, which, you know, if we can address some of the other things, the water quality impacts are going to get better, and we get EPA, Ohio EPA, US EPA off of people's backs. Some of the others, to me, I just sort of want an accurate representation. I think Molly was sort of getting at that, an accurate representation, so that we're not sort of assuming that we're getting good hydrologic function when we're not. So we can do one of two things. Let's either improve the soil and take credit for that, or let's have more bigger stormwater infrastructure to take care of what's actually happening. All right, so some actions. This is the one that I just said. I'm actually, I went looking for something that I would consider a good, accurate description of how to use the curve number. I haven't found it, and I'm actually working on this for a community in Ohio. I hope to have a draft of it done in the next couple of months, and I'd be willing to share it with people. I would love it if everybody would look at it and see what was useful for them in their own community. So I don't have something to share on that today, but soon. And I'll be in contact with Tessa and other people to make sure that that gets to people. Another thing that we just don't do, and this is because our expectations are so low and our standards don't really help with this or give credit for it. The easiest thing to do is just to go into a site and completely strip it and do mass grading. If there was some benefit to preserving some of the soils in there, if there was some way to get a credit for that, probably more of that would happen. We definitely want to restore functional soil profiles as part of the development process. This is going to require this to be in code. This is implied in a bunch of places in the rainwater manual and in the construction general permit, but it's not really enforced at this time. I'm going to get into that a little bit. There is some language available in some different places in ordinances and model ordinance. And here's a model ordinance from the Chagrin Partners, which basically says, these are our expectations about either protecting or restoring soil profile. The rainwater manual, actually, this is an expectation from Ohio EPA, but I don't know that anybody knows that your soil profile post-development is going to be restored at one of two levels. The first is topsoil replacement. A second is a topsoil replacement with subsoil decompaction. And there's some good stuff in here in what's expected, and it actually has some numeric criteria that go with it, all right? So topsoil replacement looks like this. On the left, this actually mimics what happens pretty well. You're removing the topsoil. You end up then with some sort of compacted parent material. You go through and loosen that, and then you put topsoil and or compost on the surface and mix that up, and you're creating, rather than your total root environment being 3 to 4 inches, 2 inches if you're using sod, you're getting 6, 7, 8 inches of functional topsoil, right? Going a step beyond that would be including the soil, subsoil decompaction with this, where when you run a soil ripper through this, we give the roots and water opportunities to get beyond that 6, 8, 10 inch rooting depth. I'm going to share what Stu's been working on, and I just love this graphic he created. What he wants is to be able to create an environment for superior sustainable turf. He tried to come up with a sort of a catchy phrase for that. And on the left, this is what we get. This is our post-construction typical soil. That's the soil profile right there. This is what we want. So the way that they've been working on it is by using deep ripping and using a soil spader instead of a rotary tiller, because the rotary tiller just pulverizes the soil and breaks down all of the aggregates that are there. And a spader works by lifting the soil in big chunks and mixing the compost in with it. And you actually get better distribution of the compost to whatever depth that you're working. And you can get the spaders that will incorporate the compost and do the mixing to 10 inches up to 20 inches. Does require some horsepower, but usually developers have some horsepower available to them. And so I just wanted to show this example from some of Stu's work. These are side-by-side plots on a school site. This is the soil that's been treating normally with a layer of sod put on top. And so in a 2-inch rain, that's what that looks like. Just right next to that, where they did the soil profile restoration, that's what it looks like with the 2-inch rain. Can you tell the difference between those? I think this is what we want, right? If we're going to have bigger and bigger storms, more intense storms, we would like to have the soil do a lot of the work for us like it does in natural landscapes. All right, just a couple of things on resources there. If we're going to do this, this is going to have to be a team effort where the regulators, the developers, the construction contractors, the engineers are all involved in it. So there's going to have to be a carrot and a stick. We're going to have right standards and regulations, but they're also going to have to get credit for the work that they do. And then I just want to, the last thing I'm putting here is there's a lot of ways to incorporate better soils and environment that we're already doing. And I just want to go through some of those. It helps just move catch basins into pervious space or disconnect downspouts. Grass waterways, swales are much more functional than curb and gutter and pipe. Bioretention cells, we're putting in great soils that do a lot of work for us in a small space. Dry swales, and I want to give examples of one project. This is on Sturncrest Road in Orange Village. They had a bunch of flooding here. The residents wanted them to do something with it. And so they put in drain pipe, but they're running all of that through bioretention. So you're getting the benefits of bioretention here. Just a few looking for a word, rightly located bioretention cells. And this is what it looks like now. And basically they haven't flooded the area since then. Dry ponds, dry basins done well, infiltrate a lot of water. There's a couple of examples, grass bioretention. I threw a bunch of measures in here that I think in some way we're all going to have to start tracking how we're getting soil benefits in our communities in different green infrastructure ways. And I just threw a bunch of them in here, ones that occurred to me. And I think we need to set a baseline, get out and do some measurements and start moving the needle. So that's really the end of my presentation. How are we doing? That was 86 slides in 53 minutes.
So impressive. So I'm jumping on here real quick to touch base with the Zoom folks too. We're gonna do some questions here real quick. So we'll grab some from the folks that are here. If you have questions on Zoom, you can just drop them in the chat and we'll try to get those responded to as well. If you need to drop off on Zoom or in person here too, more than welcome to. But those of you on Zoom that are looking for continuing education credits, just make sure that you fill out that document that I dropped the link for in the chat as well. And
I'm happy to stay as long as
yeah. Yep. So if you have any questions, drop them in the chat, or folks here in person can raise your hand.
So Jay, you mentioned that compaction during construction, that's one of the main hurdles here. And there was a few things that you mentioned, to do afterwards to improve